In this video, I want to provide a better physical understanding for the Coriolis acceleration. So this stems from the fact that when people learn mechanics, they often, in the first course in mechanics, see circular motion with the uniform speed, like a rod that would be swung around a rope or something like that. And then they get to the concept of the centripetal acceleration, and they understand that centripetal acceleration can be felt physically, basically by the force needed to keep that rock in a circle if you swing it around a rope, and they get kind of a physical understanding of what this acceleration means. However, Coriolis acceleration is often not covered in such courses, and when people encounter it in later courses, they use the complex math of vector calculus to come up with some terms that correspond to the Coriolis acceleration, but the physical meaning is really not often discussed because these are much more advanced courses and they're more directed to the abstract side of it. So just so that the people may not know what a Coriolis acceleration is, the Coriolis acceleration is acceleration felt by an object that's moving on a rotating disk, for example. So you have this disk that's rotating at an angular speed omega, and you have an object that's bound to, here I put it moving purely radially because we want to get a physical understanding. Does that have to be purely radial? But in this case, we have an object that's moving purely along the radius of the disk. And of course, as the disk turns, the object will need to turn because we guide the object. For example, think about a toy train on tracks that would burn around along a diameter or a radius of the disk. And we presume that this radial speed is a constant, so it doesn't change. We make sure that it doesn't change. So that takes care about the centripetal acceleration, which is taken care of separately. And the Coriolis acceleration is equals to twice the angular speed times the radial velocity, and the Coriolis acceleration is perpendicular. Oh, there should be a vector here. The Coriolis acceleration is perpendicular to the velocity of the object here in the radial direction. So the acceleration will be this way. So what's happening here? Well, this object initially moved along the disk in the first direction, and at some point later, it's got to move in another direction. Since the direction of movement changes, we need to exert a force on it or to accelerate it in the right direction. So what will happen is that if you want to take this vector and change its direction, you will need to exert a force in that direction. This is similar to what we have when we have the centripetal case, in which you have an object here that's going in this direction, and a bit later it's going in that direction, and there's a force added this way to make sure that we can change the orientation of the vector. It's the same thing but rotated 90 degrees. So that's the first thing we will need to do. We need to see what force is required to change the orientation of this vector, and this force of course will be in that direction. So if you're moving along tracks like this, and you have a toy train that's moving this way, there will be a force exerted on the train this way by the tracks. The second thing we have to be very careful about is that as you move away from the center, your tangential velocity here that's the initial tangential velocity, and the final tangential velocity, as seen from the inertial frame of reference, will be larger. So it will change direction, but it will also be larger because you are further away from the center, and we know that the tangential velocity is equals to the radial position times the angular speed. So if you move a bit further away from the center, you also need to put in a bit more force to accelerate. And since this is also in the direction perpendicular to the radial direction, you will need to exert a force in the same direction we had previously, in this direction. Now, this is very convenient because we have two effects that occur along a similar line of action. The line of action is perpendicular to our track. This means that we can add them. These are two different forces, if you want, that need to be exerted to have an effect in the same direction. It's the same that we'd have any one-dimensional problem in mechanics. You would have, for example, a propulsion force to move a car this way, and there is the drag force of the air acting this way. You can add these two things up. Well, since we are moving in, we are accelerating in the tangential direction, we can calculate the effect of these two accelerations and add them together to get our Coriolis acceleration. So let's just do that on the next board. So the first effect will be due, for example, to the fact that we are moving away from the center of the disk. So we have the acceleration. We will call this one A1, and A1 is due to moving away from the center. So A1 is equals to the final tangential speed minus, the initial tangential speed divided by a certain amount of time, delta t. This is equals to, well, at the initial moment, we will say that we are initially at a distance r, and here we will say that we are at a distance r plus delta r, a small increase in distance. And of course, this is valid if all the time intervals and distances, everything is very small. This will be the same in the next calculation. We will assume that this is the case without going into the formal vector calculus calculations, because this would in fact detract from the purpose of the video. So initially we are going at we're going at r plus delta r times omega. So that's what we had previously for the tangential speed as a function of the angular speed and the distance. And initially we were going at r omega. This is all, by the way, in the tangential direction. We don't care about the radial direction because nothing changes along that direction. And when we get these angles very small, because we want the time interval to be very small, the displacements are very small, these two vectors would be basically along the same direction. And we can just forget about what happens in that direction. And then we divide by delta t. Now our r omega here will be cancelled by this one, and we get delta r over delta t times omega, but delta r delta t is the radial speed, so that's simply Vr omega. So that's the first term, and we notice that it's half of the Coriolis acceleration, which is twice that value. So the first effect we have is we move away from the center. As we are further away from the center, we need to move faster, and to move faster we need some acceleration, which is given by Vr omega. So now on the next board, we're going to have a look at what happens when we change the orientation of our vector here. Now the second effect is due to the change in orientation of our vector. So we have the formula that the acceleration is given by the final velocity minus the initial velocity over the time interval. Now, we saw that when we went from this position to this position, the tangential velocity would be a bit larger. So initially we had like some vector here that was the initial velocity, and here we have the final velocity. And this one will be a bit larger. However, we will see that we don't really need to handle this formally, and we will just see what happens when we change the direction, for example, of VR. So we have here initially VR was in this direction, and after a certain amount of time it's in this direction. Now, we could do the calculations, but we don't really need to do it. Why? Because we know that when we change the direction of an object going at a certain velocity this way around a circle, the acceleration is given by omega v. Why is that? Because that's the formula we had for the centripetal acceleration. So it's going this way, it's going this way, and to change the orientation of this vector, of the object having a velocity going this way and this way, the acceleration is omega times the velocity. So similarly, what we will have is to change the direction of this vector here, this velocity vector Vr, to this direction, we will need to exert a force, an acceleration equals to omega Vr. Now you're wondering, why am I only taking care of Vr? What happens to the tangential velocity in this calculation? Well, remember that we are only trying to understand what's happening in this direction. Basically, what is the force exerted tangentially? This vector here, yes, there is a change in direction, but it's a change in direction caused by a radial force. So this component, if you want, of the velocity will change to this component of the velocity in the tangential direction, but the force is directed radially, and we just initially assume that we will not care about what's happening radially. So all we have to care about here is what's happening radially, and radially we can see that the change in orientation is equal to omega times Vr. So that would be V. And how do we do that? Well, I could show it, but you can look online on the many derivations of the centripetal acceleration. The calculation, it's exactly the same. You use the cosine law and find out that in the end, you're left with the term equals to omega v times the magnitude of the velocity, so the speed in the radial direction. So A2 is equals to omega Vr. And of course, the Coriolis acceleration equals to A1 plus A2 equals 2 omega Vr. And that's it for today.